Welcome to our quantum deep dive.
Glad to be diving in.
Today we're tackling something really groundbreaking, the quantum search algorithm developed by Lov Kumar Grover.
A huge name in the field. And we're using Jorgo Schneppet's essay as our guide here.
All right, so before we jump into Grover specifically, maybe a quick reminder. Quantum computing versus classical.
Definitely. So, your standard computer uses bits. They're either a 0 or 1. Simple.
On or off.
Exactly. But quantum bits or qubits, they're different. They can be 0 or 1 or, crucially, a sort of combination of both at the same time.
That's superposition, right? Like the spinning coin analogy you often hear.
Precisely. It's in this state of possibility, holding more information potentially. And this allows quantum computers to tackle certain problems much more efficiently.
Okay, so it's not just about making things faster across the board, but about a whole new approach to computation.
Absolutely. And Schneppet's essay points out this has implications far beyond just, raw processing speed. We're talking cryptography, simulating molecules for medicine.
Material science, biotech. The list seems pretty long. The potential impact feels enormous.
It really is. And Lov Kumar Grover is a central figure in unlocking that potential.
His 1996 algorithm, Schneppet calls it a landmark.
It truly was. Grover addressed a really fundamental problem. Searching through an unstructured database. Think of a huge list with no index, no order.
Like finding one specific name in a massive unsorted phone book by hand?
Exactly.
Yeah.
Classically, you basically have to look, on average, through half the entries. We describe that complexity as ON proportional to the size N.
So double the size, double the search time, roughly.
Pretty much. You might get lucky and find it first try, or unlucky and find it last, but on average it scales linearly.
But Grover, he found a quantum way around that.
He did. And this is the amazing part. His algorithm can find the item you're looking for in roughly the square root of N steps, so ON.
Square root. That's a huge difference, especially for large N.
It's a massive quadratic speedup. If N is 1,000,000, the square root is only 1,000. It's the kind of leap, as Schneppet stresses, that's only possible because of quantum mechanics.
Wow. Okay. Now, this isn't just a theoretical curiosity. Schneppet mentions real applications.
Oh, definitely. Think about database searching, obviously, but also data analysis, optimization problems, and maybe most famously, its potential impact on cryptography.
Right. Breaking encryption often involves searching for keys.
Exactly. So an algorithm that speeds up searching could pose a threat to current systems.
So our goal for this deep dive, guided by Schneppet's analysis, is to really get under the hood of Grover's algorithm.
Yeah, we want to understand how it works, the quantum principles involved, and, importantly, why it's such a big deal for quantum information science.
Schneppet lays out a good path for us. We'll look at the quantum mechanics, the math behind it.
The challenge isn't actually building the hardware to run it, which are, significant.
True. And then dive into those applications, cryptography, data analysis, and maybe peek at the future research it inspired.
Exactly. The aim is to really appreciate Grover's contribution, his scientific legacy, and what Schneppet's essay tells us about its ongoing relevance for quantum tech and society.
Okay, let's wrap up what we've covered today. Reflecting on Jorgo Schneppet's insights, the core takeaway about Grover's algorithm is that incredible speed up, right?
Absolutely. Going from ON, classically for unstructured search, down to ON quantumly, that quadratic jump is just fundamental.
And it achieves this using uniquely quantum tools, things like amplitude amplification.
And quantum interference.
Yeah.
It's about carefully manipulating probabilities in the quantum state to boost the chance of measuring the answer you're looking for.
It really shows how quantum mechanics lets us break through barriers that seem absolute in classical computing.
It does. And Schneppet's essay really drives home the significance. It's not just abstract theory. It proves quantum computers can solve practical problems far faster. And it's had a huge ripple effect, particularly in fields like cryptography.
People realized, okay, these machines could actually break things we rely on.
Precisely. It spurred a lot of research into quantum-resistant cryptography.
And it's exciting to see the hardware catching up, slowly but surely. Schneppet mentions technologies like superconducting qubits, ion traps.
Yeah, the engineering challenges are immense, but the progress is undeniable. We're getting closer to machines capable of running algorithms like Grover's on meaningful problem sizes.
Looking ahead, Schneppet points to a really wide range of future uses, too.
Oh, absolutely. Medicine, for instance, searching huge genomic databases for patterns. Chemistry, speeding up molecular analysis for drug discovery.
Materials science, designing new materials by simulating quantum interactions, even quantum machine learning.
The potential is vast. Grover's work really opened a door, and researchers are still exploring all the rooms beyond it, pushing quantum information theory forward.
It definitely leaves you thinking, what will the world look like when this kind of computational power becomes readily available? It feels like we're right on the cusp of a genuine quantum revolution.
A fascinating and perhaps slightly daunting thought to end on.
Indeed. Well, thank you for joining us on this quantum exploration. And a big thank you again to Yorgo Snepet for the essay that guided our deep dive into Lov Kumar Grover's revolutionary work.